So, we will consider flow field with the vorticity distribution. We have already defined the vorticity as curl of the velocity vector, and in case or this vorticity is just part of the motion, we have considered that part of the velocity to be u v. Okay. So, of course, the other parts have no rotation. The other parts that is associated with that rate of expansion or the uniform flow or with deformation without change in volume, none of them have any vorticity associated with it. So, what is curl of u v? Eventually, it is curl of the total velocity also. So, curl of u itself is same as the curl of u v, and which we have defined as omega. Okay. And since the other parts do not have any curl with it, okay, because this u e and v, u e is associated with rate of expansion which is irrotational. So, that curl of that is 0, and similarly v, which is associated with the uniform motion plus straining motion without change in volume, that also has no rotation. So, the rotation of curl of the total velocity itself is curl of u v, and that is omega. And since vorticity is curl of a vector, its divergence is 0. This is an identity. Then we defined what is a vortex line. There is a line which is tangent to the vorticity vector at all points, that is what is a vortex line, and we defined what is a vortex tube. If we imagine a reducible curve within the fluid, then all the vortex line passing through that closed curve forms a tube, and that tube is called a vortex tube. So, the vorticity vector is always tangential to the vortex tube also, and the vortex lines can be mathematically expressed again by a similar type of expression equation which we earlier obtained for streamlines. If you remember that for streamline we had the velocity vector is tangential to a streamline. So, we made u cross d l to be 0. Same thing we can make again omega cross d l equal to 0, and that will give the equation of the vortex lines. Now, consider a closed curve surrounding the vortex tube once. Okay. That is, it is looping the vortex tube just once. Then the surface that is formed by this closed curve is basically an open surface, because it does not include any volume, and the integral of this vortex over that area, which we can define as omega dot n d a and we will try to show that this quantity is constant, it will not change along the length of the vortex tube, it will not change. This can be shown very easily like this. To show this, we will be using this equation, divergence of omega equal to 0. Now, how to get divergence of omega from this relation? See, this is an area integral. Okay. If we convert it to a volume integral, then that integral will be of divergence of omega, but you see there is a restriction or requirement to apply that condition, which is divergence theorem or Gauss theorem, that you can apply the relationship between a volume and an area if that area encloses that volume. Okay. So, now we have to think about an area which encloses a certain volume. Now, let us consider this vortex tube, think about this is a vortex tube, okay. And consider two such area here, one here and say another here. Along with it, consider this part of the tube, that makes a volume. So, now we can apply this divergence theorem for the surface of this, we can call it a cylinder, of this cylinder and the volume of this cylinder. Okay. See this, whenever you try to apply divergence theorem, you must be very clear that the relationship between that area integral and volume integral is true, provided that area encloses that volume, not just any area and any volume, you cannot apply that condition. Okay. So, now let us call this area, this one let us take it A 1, this as A 2 and this area of the tube, surface area of the tube, we call it say A W. So, now the total area is sum of these three, okay. And the corresponding normals we can call it here as N 1, N 2, and let us say a normal to this N. Now, apply this area integral here. The total surface integral is omega 1, we are taking the value say here omega 1, okay, and omega 2 here, N 1 d A 1 integrated over this area A 1 plus okay. This is by application of the divergence theorem is divergence of omega d v, where this entire volume is V. Okay. Now, since divergence of omega is 0 for all choice of volume element, it is 0 everywhere. Okay. So, this total integration is 0, right. Now, you see this third area integral omega dot n d A integrated over this surface. Now, since this is a vortex tube, all the vortex lines are tangential to this. So, there is no vorticity which is normal to this area. By definition, all vortex lines are tangential to the vorticity vector. Consequently, there is no normal component of vorticity to this surface. Hence, this integral does not contribute anything to this. So, this is also 0. Okay. Because omega is tangential to this surface. And since these two normal, what we have taken, both the normals taken as outward, okay, but they have different sense. The two normals have, two outward normals have different sense. So, this integration now become okay. and the choice of area is also immaterial. We can choose any area, any type of area. Any area means any type of area, whether this area is a cross sectional area or in some inclined area, does not make any difference, because ultimately that n dot d a will take care of it. So, these remain constant along the vortex tube. This is called as the strength of the vortex tube. So, you can summarize this result, that the strength of the vortex tube remain constant along its length. Of course, it has the consequences then, that a vortex tube cannot end within the fluid, because if it ends means its strength is changing, its strength is becoming 0, but that it cannot happen, the strength will remain constant. So, a vortex tube will not end within the fluid. It can either end at the boundary of the fluid if the condition allow it, or it can form a closed loop. A vortex tube can either end in the boundary of the fluid, or it can end in a it can form a closed loop. And also that all the material elements which passes through or which makes up the vortex tube at certain instance will continue to make the vortex tube at all subsequent times. All these are result of this simple thing, and these results together are known as Helmholtz theorems on vorticity. That the strength of a vortex tube remain constant along its length. A vortex tube cannot end within the fluid, it may end either at the boundary of the fluid, or it may form a closed loop. And the material elements that makes up a vortex tube will continue to make the vortex tube. So, remains the material fluid element Now, think about an idealization of this vortex tube, idealization of the vortex tube. Think that the cross sectional area of the vortex tube continue to decrease, but in such a way that integral omega n dA or the strength remain constant. Then in the limiting case, what we will get? We will get a curve, we will get only a line. In general, it is a curved line, and that is called a line vortex. That is called a line vortex. Be careful about the difference, vortex line and line vortex, they are not same thing. Vortex line is any line which is tangential to the local vorticity vector, that is vortex line. This is a physical quantity. In flow, there are really vortex lines. Okay, you may not be able to see it, but with special treatment you can see it. There are technique by which you can see it. So, they are real line vortex lines, but this line vortex is just a mathematical idealization of a vortex tube. It is just a mathematical thing. So, vortex line and line vortex, they are different, do not confuse with the two. And say, before moving to that line vortex, if the cross sectional area is infinitesimally small, okay, then the strength of that vortex tube can simply be taken as the product of that cross sectional area and the vorticity. Now, see it in other way. Think about that same open surface A that we are considering. For an open surface, area integral over an open surface, that is omega n dA, where this A is an open surface, sorry. That means, it is not enclosing any volume. This area is not enclosing any volume, just like the cross sectional area, what we consider A1 or A2 earlier cases, any of them. This integral can be converted to a line integral. Can be converted to a line integral. You know the relationship? Let us say the relationship, if we have a closed curve, and we integrate a vector around that curve, which can be written as, say, let us say the general vector A, and say the length element we call it dl, integrated over this closed curve is equal to the curl of A n dA. Oh, I think we should have taken some other, let us take the vector B, so that there is no conflict of A. Okay. That is the relationship known as Stokes theorem. Known as Stokes theorem. So, in this case what it will be? Omega dot n dA or we since we are writing u v, we will write u v, that vortex part, that we will just write dx, where C is the curve, that is the boundary of the area A. C is the curve which is boundary of the area A. This integral or integral of any vector about a closed curve is usually called the circulation. So, this is what is circulation. So, what we get, that circulation around a closed curve, that closed curve lying on the vortex tube, circulation around a closed curve lying on the vortex tube is equal to the strength of the vortex tube. This itself we have already defined as the strength of the vortex tube. So, circulation around a closed curve lying on the vortex tube and passing it once is the strength of the vortex tube. Another very important quantity in fluid mechanics, circulation, and you will see how useful it is, at least in aerodynamics, of course later on. Next, we will consider the velocity field due to some special type of singularities in vorticity distribution. The one and very common singularity is where we have a very large concentration of vorticity near a line, and everywhere else the vorticity is say 0. Of course, this line has to be parallel to the direction of vorticity, otherwise the divergence of vorticity will not be satisfied. Once again, we can make that mathematical idealization, that if we have a very high concentration of vorticity near a line, we can now assume that that region near the line is being shrink to the line, and all the vorticity is placed on the line itself, all the vorticity is about that line itself. This is then a singularity in the vorticity distribution. Nowhere else there is vorticity, but around a line there is a very large concentration of vorticity. And let us say that the strength of which you have called line vortex. This is of course a singularity in a vorticity distribution. Later on, you will see that in many practical flow problem, this type of situation occur, where there is a very strong concentration of vorticity just about in a narrow region, which can be thought of as if a line. Okay. That sort of situation comes in many practical problem. So, in that respect this is quite important. Let us say the strength of this vorticity distribution is gamma. Okay. Then what will be the velocity associated with this vorticity distribution at some point somewhere away from this line? We have already derived that relation. If you remember what it is, u v equal to how much, 1 by 4 pi r cross omega dv by r cube. Yes. Minus 1 by 4 pi. Okay. Now, this since we have a line here, so consider a vector line element d l, then this omega d v can be written as gamma d l. Yes, and the integration will be on the length. So, we now have that is all right. Now, for simplicity, consider this line to be a straight line and this gamma to be constant everywhere, uniform vortex distribution about a line. So, considering straight line vortex, Now, to carry out, let us consider this line, say from minus infinity to plus infinity. Consider this small line segment here somewhere d l, and let us say the point is here. So, what will be the direction of this velocity? You see, the direction of the velocity is always azimuthal about this line. This will be the direction of the velocity, and the magnitude of this velocity can be obtained as not a yes.
So, how can you take L as means line is infinite? And this
Huh.
is infinite. So, what is L then?
This length is L. It is changing from minus infinity to plus infinity. So, you see, the velocity at a point simply depends on the perpendicular distance of that point from the line. Similar thing as we obtained for a line source, if you remember that for a line source also we had a similar sort of velocity distribution. And the direction is in the sense of, you see, this could have been very easily obtained by the definition of that circulation. You can obtain that, you apply that circulation definition of that circulation, what we wrote earlier, omega dot n dA equal to u dl or u dx. Use that, consider the curve to be a circle, and you see that you can very easily get this relation straight away, that omega dot n dA is simply this gamma, and when you take a line integral, since this velocity has have symmetry at all point about a circle, the velocity magnitude will be same. So, that u v dx will be simply u v into 2 pi s, what you have written. So, gamma equal to u v into 2 pi s, a very straightforward application of that relation. Now, this is of course, a solenoidal velocity field, correct, the way rate of expansion produces a irrotational velocity field. Similarly, a vorticity distribution produces a solenoidal velocity field. The velocity field associated with pure vorticity is solenoidal, and we can define a stream function associated with this velocity distribution. A stream function from the definition. This is, if we think in terms of a polar coordinate, this velocity is the tangential velocity, azimuthal velocity. So, it is u theta, which is minus d psi dr, okay, or we should call it minus d psi ds, because you have taken s as the coordinate. So, minus d psi ds is this what is gamma by 2 pi s. So, what is psi? Yes. So, that is the stream function associated with this infinite line vortex. And what is an infinite line vortex of uniform strength? Is a 2-dimensional point vortex. So, this is often called a 2-dimensional point vortex. What we have called an infinite line vortex is often named as, or most popularly called as, 2-dimensional point vortex. Okay. So, this is 2-dimensional point vortex. Now, one very important question which has not struck you, but when you, if you remember that when we obtained earlier that expression for the vector potential B in connection with the vorticity distribution, we said that B v has to be solenoidal, and that is possible if a certain integral omega dot n becomes 0 at the boundary. If you look to your earlier notes, you will see that that was a requirement. Under that condition only all those solutions are valid. But in this case, or this line vortex as extended to infinity, assuming that the boundary is at infinity, that is, it is only fluid only, there is nothing else. Then at infinity it has not satisfied that condition. Then how it is possible to use all these relations that we have used here? Yes, it is possible by a simple artifact, that this line extending from minus infinity to plus infinity, we can close this line by, say as an example, by considering a semicircular arc from that minus infinity to plus infinity. So, that this vortex line forms a closed loop of infinite radius, and then that curved segment, that arc, semicircular arc, being at infinite distance away from any point, we will have practically no contribution to velocity at any point. So, the result remains valid, but we have to remember that this line vortex we have actually closed even though we have not stated it explicitly, but it is closed by say a semicircular arc, or we can even think about a rectangle from that infinity to extending in other direction. So, that all the segments are far away from any point at infinite distance away from any point, hence has no contribution to it, because the velocity field in this case is decreasing as the distance increasing. Okay, now let us consider another very important thing, are seat vortex. That is, we have let us say an infinite seat on which there is a concentration of vorticity and everywhere else it is 0. Later on you will see this is a simplest model for an aircraft or aircraft wing, just a seat vortex. The complete aircraft wing can be thought of as a simple seat vortex, and assuming it to be seat vortex, we can get the important parameters that are usually required. For a wing, see, for an aircraft we want to know what are the forces and all, you will see that some of them at least can be obtained just by considering the wing to be a simple seat vortex. So, here even though we are considering this is just a simple mathematic basic problem, but they have very wider applications which will come sometime later. Okay. If not in this course, maybe in the next course, because some of the things we may not be able to cover in this course, which will be covered in the next aerodynamics course. Now, in this case we will define the strength of this vortex seat is defined by this simple integration where dn is distance normal to the seat, and we may think that this integration is carried out over an infinitesimal distance. Just considering a two dimensional representation, just that okay, this represents the seat, then we can think that okay, we have integrated from here to here this. We will call it, say this is epsilon. So, this is integrated over epsilon. And then as epsilon approaches 0, but this is now a vector. And the strength of the seat vortex is now. Let us see what would be the velocity field associated with this vortex distribution. Once again, that u v can be written as Okay, all these are functions of position as well as time, which you are not writing all the time explicitly. But remember that all these parameters are functions of position and time x, y, z, t, which you are not writing explicitly most often. This will be how much? Minus 1 by 4 pi into r cross omega, but we can now change it, because that omega dV can be written as okay. Now, first of all, consider that the strength is uniform. Consider the strength to be uniform. This can be written as just a mathematical manipulation. Just a mathematical manipulation. And the result is n is a unit normal to the seat vortex, and it is directed to the direction at which the point lies. This u v, the velocity we are finding, this is of course at a point. Okay. We could have written it this u v is at a point x. So, n is normal to the seat vortex, and directed to the side at which x is. See, the magnitude of this velocity is simply half gamma, magnitude of this velocity is simply half gamma, and for uniform gamma, that is constant gamma, half gamma is constant everywhere. So, if we consider one side of the seed vortex, on that side the velocity is half gamma, it is of course from here it is parallel to the seat, the direction of this velocity is parallel to the seat as well as perpendicular to gamma. This velocity direction is perpendicular to the gamma and parallel to the seat. Now, if you consider the seed vortex on the two sides of the seed vortex, you see the on the both side the magnitude of the velocity is same, half gamma, but the direction is different or sense is different. In both cases it is parallel to the seat, but since the n is in different direction. So, considering say the two dimensional representation of this seat, it is if it is half gamma like this, on this side it is this, sorry, same half gamma. So, what do we have now? That across this seed vortex there is a jump in this velocity, the velocity component which is parallel to the seat suffers a jump by a magnitude of gamma, which is the strength of the seed vortex. So, if you know some physical situation where there is this type of possibility that there will be a jump or change or discontinuities in this tangential velocity, you can model that situation by a seed vortex. If it is say from physical consideration, we can think that okay, here it is expected that there will be a discontinuity or jump in this component of the velocity. Okay. We can model it by a seed vortex, that okay, that as if there is a seed vortex there, and eventually see this is what an aircraft wing does, it creates a difference in velocity on the upper surface of it and the lower surface of it. Okay. So, it can be modeled by a seed vortex. If the strength of the seed vortex is not uniform, that is perhaps a more general case, the strength of the seed vortex is not uniform, then you will find that this relation still applies, but locally, because that gamma is changing. So, at each and every point the difference will still remain gamma, but since the gamma value is different, the u values are also different, but again that locally the jump of gamma still holds. Another very useful case perhaps you could have been obtained, or you may try yourself, assuming this seed vortex to be a cylindrical seed vortex. The result is known to you, you have done it. Think about the velocity to be the magnetic field and the vorticity to be the electric current. You have done that, no? A cylindrical tube or solenoid. What happened? There is electric field inside, but not outside. You will find the same thing here also. If you consider a cylindrical vortex tube, you will see that the velocity in the axial direction within the tube 0 outside. You may try that problem. One thing I should mention in this case, though we have not done it, perhaps we will be doing it later. A seat source distribution, a surface distribution of source I have mentioned, but I have not found the velocity. If you evaluate it, again you will see that that creates another jump but not in this tangential velocity, normal velocity. If a source strength of m is placed over a sheet m per unit area, strength distribution of m placed over the surface area of m, then it will create a jump in normal velocity by an amount of m. That will be required in some later time, we will do it at that stage. Okay.